thanks. So I was asked to give this lecture today on weather resources because it's going to be a really key part of the new Centre of Excellence. There's not actually a huge amount of research that goes into this specifically, so I'm mostly going to be, instead of really delivering a lecture, it's kind of more of a research presentation on some of the work that I've been doing, but I will also introduce the topic in a more general sense as well. So weather resources, we think of this as how is weather an opportunity, and that's both in the current climate and in the future climate. So a lot of our focus is on what's going to happen with climate change and some of the high impact things that could affect the way we live our lives. But we can also try and reframe this potentially as an opportunity for seeing how the weather might change and whether there are kind of new spaces that will open up as a result of that. So it is a bit of a shift from thinking about extremes in the usual way that we do. CLEX is the Centre of Excellence for Climate Extremes, so weather resources doesn't have to be looking at things that are in the tails of the distribution. It's more about kind of utilising things as a resource, whether that's in the tails or in the bulk of the distribution. So the kind of questions that you might ask when you're thinking about weather resources are, what do Australia's current weather resources look like? So if you imagine a map of Australia and you try and map areas that are particularly useful for certain sectors, and their usefulness comes as a result of the kind of weather conditions that are there. And then thinking about climate change, how can we better anticipate future weather resources? So as the climate changes, will there be new areas opening up that we could make the most of? So you've probably seen a breakdown of the new centre projects, is that right? Yeah. So yeah, this slide is just to kind of emphasize how front and center weather resources is. It's right up there with weather system dynamics, high impact weather. These are all key components of the new center, and weather resources is there. So I'm going to throw to you first, have a think about what kind of sectors you might associate with requiring weather as a resource. I'm going to show a couple of slides in a sec that have maybe 5 or 6 different sectors. But if anyone has any ideas now, please shout out. Angela? Nuclear. That's not coming up on the next few slides. How is nuclear? Would you like to expand on that a bit more?
They require a lot of cooling from water, and France ran out of water last year because there was not much rain, so they had to sort of ramp them down.
That's a good one. Yeah, okay. Hydropower, yeah. So I'm going to be talking about renewable energy for most of this talk. Hydropower will be in there. Any others? Yep, wind power, yep, totally. Agriculture, yeah. So rain-bearing weather systems, that kind of thing, evaporation, yeah. Tourism, yeah, that's a big one. So that's a link to the economy as well, so people come places because of nice weather.
Solar sector?
Solar sector, yeah, this is good. You're all talking about the renewable energy stuff, so it shows what I'm talking about is going to be interesting, hopefully. Right, one more. Okay, so what did I put down? Water resources in the bottom left there. So this is a big one as well. So our water supply in our cities usually comes from reservoirs, right? And that relies on rainfall and evaporation and the kind of the integral of various different climate processes that ensure adequate drinking supply. Agriculture, we've already mentioned. Health and well-being as well. So you can think of weather as a resource for this. We're very used to thinking of it from a kind of negative aspect, like are the pollution levels too high in our cities? And we know that clean air is linked to a healthy and longer life, so you can think about weather as a resource in that respect. Ecosystems as well. The reason that we have such specific ecosystems is because of the kind of unique weather patterns there that link with the unique geography. So climate change will impact the way that these ecosystems, and of course, that's also linked to health and well-being as well, because we know how important it is to get out into nature. Renewable energy, transport as well. So I'll talk a bit more about transport, but Aeroplanes tend to make the most of the way that the weather systems are moving around the world in order to save fuel, and tourism as well. That was a good one. So transport, the reason I'm going to talk about transport for a few slides is just because when I was researching this presentation, I found this kind of interesting. But if you think back to the age of sail, people have been making the most of weather patterns to save themselves time for a really long time. So this is a map of the trade winds from the 17th century. The trade winds, as I'm sure you know, are those kind of belt of winds that travel from west to east. And people use these in navigation for hundreds of years. This shows the kind of typical routes that I think Spanish and Portuguese sailors would take when they were sailing around the world. And you can see for some of these routes, they look like they're going in a really strange direction. So, I don't think I have a pointer. So,
just to your right.
Yeah. Yeah. So this one here, if you look at the route down from Lisbon all the way down to South Africa here, you can see that it doesn't just skirt along the coast of Africa. And that's because they found it very problematic sailing into the headwinds of the trade winds. So they had to go almost all the way out to South America in order to save time. And then the planes that I mentioned as well. Planes often make the most of the jet stream in order to save fuel and save time. But most of what I'm going to be talking about is on renewable energy because that's my area of expertise. I'm going to talk about different types of renewable energy resources, and we've got a good head start on that already. Mapping the resource variability around Australia. So this is a kind of core concept when we think about weather as a resource. We're not just interested in whether it's a resource in one particular location. We're interested in the kind of general availability for individual nations. Then we can do some interesting things like look at the kind of weather patterns or weather systems that might come with weather as a resource or impact to weather as a resource. And then linking nicely to Claire's talk, I'm going to be spending quite a bit of time looking at the kind of seasonal variability and the way that the climate modes of variability interact with renewable energy generation. So a few different kinds of renewable energy. We had hydropower mentioned earlier. There are a couple of different kinds of hydropower. The most important one for weather as a resource is this impoundment style. An impoundment is basically just a reservoir. So the water is provided to the reservoir through rainfall and through runoff and all those integrated processes. And then you have to worry about things like evaporation taking away that resource. And then when you have enough, when you have the demand for electricity, you just dump the water down and the turbine spins and you generate electricity that way. And pumped hydropower is something that's seen as being quite important to Australia's future energy mix. Pumped hydro is interesting because this is kind of a bit away from weather as a resource because you're not requiring any sort of weather to power these systems because it's a closed loop system. You release the water into another reservoir, that generates your electricity, and then when the price of electricity is low, you can just pump it back up to the original reservoir. So it's a closed loop system. So yeah, the kind of variables that we're thinking about for impoundment is this rainfall and evapotranspiration and evaporation, and things like that. Solar power, rooftop solar is everywhere in Australia now, so we're generating power right over our homes, which is really cool, and that's going to be a key part of the energy mix too. But if you've driven out into the countryside, you might have come across these really large-scale solar farms as well. So it's not just on our rooftops, we also have these huge farms generating solar out in the bush. So the kind of climate variables that we're interested in when we think about solar power, of course, these things are powered by the sun's radiation. So solar radiation is a key variable there. And the kinds of things that impact the amount of radiation that is received by these solar panels are things like cloud cover, so how cloudy it is, and also pollution levels there as well. So these things reduce the amount of radiation that's received by the panel. And temperature as well. Solar panels don't operate particularly well under high temperatures. So during a heat wave, you might expect that the increased level of electricity that homes require would be balanced by the increased availability of solar energy, but actually the high temperatures make the solar panels less efficient. So that's something you've got to consider. Offshore and onshore wind, so pretty simple ones. You would have seen these everywhere. Various different kinds of turbines that harness the power of the wind in different ways depending on where they're situated. So the offshore turbines tend to be a lot bigger because the wind is a bit more consistent out there, and so you can get higher wind speeds. But you've got to watch out for when it's too windy as well. So wind turbines have to shut down when the wind speed reaches a certain threshold. Otherwise it causes damage. So we've got three main kinds of renewable generation there. So this is already becoming like a bit of a complicated problem when we're thinking about energy supply. We've got wind, we've got hydro, we've got solar, and these come with a whole bunch of different weather or climate variables that you've got to consider. Okay, so we're getting into the kind of multivariate space now. And then if you think about, well, we're not just interested in how much energy can we generate, we're interested about matching that to demand. Okay, we don't want to generate energy when there's no need to. And demand comes with its own set of weather variables that influence the level of demand. So temperature is the main one. The temperature determines the extent to which we need to heat or cool our homes. But also how we feel is not just related to the temperature, it's also related to the feels-like temperature, which comes from things like humidity and wind speed, cloud cover as well. So we're looking at a very kind of highly multivariate problem here. If we're thinking about the impacts to us in society as a result of energy supply and demand, we've got to think about all these different variables, okay? So we're already in this kind of compound events world. But your solar farm is not in the same place as your wind farm, which isn't in the same place as your hydropower plant, and they're all not in the same place as where you live. So we're not just thinking about lots of different variables in the same place in the kind of traditionally multivariate setting. We're thinking about how these things interact over really large spatial scales and in time as well. So when we're thinking about kind of impact-focused climate science or weather science, we've got to consider all these different sort of interacting effects. So getting a bit more into the detail of the electricity system, this picture gives you an indication of the extent of Australia's electricity markets. So every state except Western Australia and the Northern Territory falls under something called the National Electricity Market. And that's got it's one of the longest power networks in the world. It's got something like 40,000 kilometres of transmission lines. And then Western Australia and the Northern Territory have their own systems. But we'll be talking about the National Electricity Markets today. These red polygons there, they give you an indication of where has been, of places that have been identified as having high resource potential for solar or wind and hydropower as well. So that gives you an idea of the kind of spatial extent that we need to consider when we're thinking about supplying energy. This is basically showing the same thing, this map, but kind of color-coded according to whether these regions are kind of mostly identified as useful for solar or wind, or in some cases both of them. And the next few slides that I'm going to be showing you are all based on some work that I've been doing that uses the ERA5 reanalysis data set to look at variations or deficits in wind speed and solar radiation. So we're kind of moving away from a purely resource perspective, because we're going to be looking at this in the context of droughts. Although we're defining droughts here as anything below the 25th percentile, so it's not really an extreme still. We're talking about 1 in every 4 days. So really simple kind of summary maps we can generate from this. If you look at panel B there, that's showing you the frequency of solar droughts for these different regions here. The red tells you that those droughts are more frequent, and the blue tells you that they're less frequent compared to the national average. And you can see we've got a really unsurprising result here that you get more blue in the north. So your solar droughts are less frequent in the north, and that's not a surprise because you get more sunlight up there because of the latitude. And you get a similar kind of split with the wind droughts as well, but it's more of an east-west split here. You can see that regions in the southwest, they tend to experience fewer wind droughts than those in the east, and that's again because of the location of the westerly belt, that kind of brings those windy systems over the south of the country. And then the compound, which is when you get a solar and a wind drought at the same time, you get a bit of a mixture of those drought signatures, but it tends to be weighted more towards the kind of solar side of things. But like I said before, we're not really just interested in droughts that happen in one location. If we're thinking about an impact to the energy system, then these droughts have to occur across multiple regions for them to matter. So what these pink and green PDFs there show is how often we might expect multiple regions to be in drought at the same time. And you can see from that kind of bulge around 8 or 9 regions that the vast majority of days you have up to 8 or 9 regions that are experiencing a drought in any one day. So these kind of co-occurring droughts are nothing unusual. It's more about the extent of how many regions are in drought that's important. So looking out to the tails of these distributions when you can get sort of up to 40 regions that are experiencing a drought at the same time, that's when your problems might occur. And we can break this down by season as well. So these PDFs now are split according to the drought type. You can see from the orange PDF there that in the winter it's really common for a lot of your regions to be experiencing a drought in the same day, and that's because a lot of your regions are in the south and there's not much sunlight not much daylight in the south in the winter. And you can contrast that to the summer situation there, where you can see that solar really isn't that much of that widespread a problem. Whereas the wind, so if you look at the blue PDFs across those 3 panels there, you can see that it doesn't vary that much throughout the year. And then the purple as well, this is kind of interesting because it really pulls out winter as the most problematic season for when you're considering wind and solar at the same time. And this is something that energy companies recognize as well, that at the moment, in a kind of more fossil fuel powered energy system, the summer poses the biggest challenges because heat waves are the kind of biggest drivers of energy demand. But in a more renewables focused world, it's going to be generation that's a bit of a problem in the winter, so that might be when the problems happen. So I think you guys have been looking at a lot of weather charts and stuff, and I'm sure that you'll have more expertise than me on analysing these kinds of things, but something I tried to do in some work was to take a look at the sort of general weather systems that come with different kinds of droughts. So here I'm plotting the cloud cover anomalies in the shading there, and the wind speed and direction in the arrows, just to kind of get a very broad scale picture of the sorts of weather systems that might be bringing these kinds of droughts to the national electricity market. So the only thing I really want to highlight here is if you compare panels B and C, if you look at the wind vectors, you can see that they're almost identical across both. And what we're seeing is this anticyclonic flow over Southeast Australia. So what that means is during our times when we have a lack of wind, we see a big anticyclone over the southeast of Australia. Big surprise, right? And then if we look at the compound drought, so this is when the wind and the solar is low, we see essentially exactly the same pressure system there. But the big difference is we have a lot more cloud during these events. So I haven't unpacked as to why this might be, but we're seeing essentially the same kind of circulation pattern between wind and solar and wind droughts, except there's a lot more cloud cover in those compound droughts. And getting into the seasonal variability as well, so this is, I guess for the rest of this talk, this is kind of going to link quite nicely with Claire's presentation. This is talking about composite analysis, right, which Claire was discussing. So here we're taking the 7 years between 1950 and the present day that have the most spatially extensive droughts for our different drought types and for different seasons. And we're plotting the sea surface temperature anomalies during those years. That's in the shading, and then the mean sea level pressure anomalies in the contours there. And the reason that we do this is to get an indication as to whether there may be some kind of large-scale climate patterns, for example, El Nino, La Nina, whether these things maybe have an influence on the variability of our droughts. So kind of obvious things to pick up here. If you look at the red boxes on the top row, we've got these kind of strong negative pressure anomalies over Antarctica. So this is maybe an indication that the southern annular mode has something to do with this. And actually Gemma's question from the previous talk leads really nicely into this, because Claire was mentioning about how you can't just go from looking at El Nino, La Nina, and then looking at your sort of surface variable, you should also do it the other way around. So on the bottom here, we're looking at the PDFs of the climate mode indices and then plotting the individual values of those indices during our 7 years that we've composited on in the top row. So we're looking at it from both directions here. The top row is showing droughts, and then you composite your climate on that. And in the bottom row, we're looking at the climate and saying, okay, where do our droughts sit within that distribution? So taking this SAM example here, you can see here this is potentially an indication of a positive SAM. And then if we look at the purple dots here, we can see that most of those purple dots sit in the upper tail of our distribution. So this is an indication that the signal that we see going one way is reflected in the signal we see going the other way. On the other hand, we see an almost identical looking signature in the composite for solar droughts, but our orange stars here are distributed kind of throughout the SAM index distribution, and it looks like it's just a couple of extremes that are dominating this composite here. So it's important to check both ways round if you want to kind of try and nail down that teleconnection. And a similar story for this kind of La Nina signature as well, right? If we just looked at this map, we might think La Nina was important for driving up the occurrences of solar and wind droughts. But actually, if you look at the distribution of these within the wider climatology, you can see it's maybe just a couple of years that are kind of dominating that signal. But one of the reasons this signal might be a little bit masked is because here we're looking at the number of droughts computed across the entire national electricity market, which, as we know, is a very large region. This is, covering from the sort of northern subtropics down to the southern extratropics. And we know that some of these climate modes have different teleconnections to Australia's climate, depending on the region and the season. So what we're doing here is we're saying, okay, well, if there is a signal, if there is a relationship between ENSO and wind or solar, then we're really going to go hunting for it. So what this is showing is the frequency of our droughts during ENSO positive phases minus the frequency of those droughts during ENSO negative phases. And so we're looking at the difference between those two. So this is not something that would actually occur, but this is really trying to search for that signal. And you can see here all of this blue shading. What that's telling you is that the frequency of droughts during La Nina is higher than the frequency of droughts during El Nino. And this makes sense with what we understand about the impacts of La Nina. You know that it's associated with rain, and of course that comes with cloud as well. So no surprise there. And we can do the same thing for the other climate modes as well. And the point here is not to go into excruciating detail about the various intricacies of where the teleconnection occurs, but just to highlight that these climate modes do have very very spatially variable teleconnections to surface climate, and it's important to kind of go through the motions of seeing where these differences might arise, and don't just consider the entire region that you're interested as a whole, but look down into the detail. But when we're thinking about impact-focused climate science, one of the problems with what I've just shown you is I've just been looking at the variables as they come from ERA 5. So we're looking at the physical climate variables. And this is not really an impact-centric metric. What we actually want, if we're interested in energy generation, is taking a look at the actual power output that we would gain from the variations in the wind speed and the solar radiation. So we can define some simple metrics, some simple energy generation models. There's something called the capacity factor, which is a really simple measure. It's just the actual energy output divided by the maximum energy output, expressed as a percentage or a ratio. So if you have a value of 1, that means that your system is operating at maximum capacity. And then you can take your time series of your wind speed, you can put it through a capacity factor fit, which for a wind turbine will look something like this. So as the wind speed increases, at some point where this dashed line is, your turbine will start spinning, and then your power will increase with the cube of the wind speed until it reaches a certain wind speed, and then your turbine can't spin any faster. So it stays spinning at the same rate until the wind speed gets too high and the turbine just has to shut down. So this is a really simplistic way for how to convert wind speed into wind power. And we can do a similar thing for solar as well. Solar is a bit more complicated because we have to take into account the temperature, but this is essentially showing that the capacity factors as a function of both the temperature and the radiation that's received at the panel surface. And you can see that the capacity factors are the highest here. So you want your solar radiation to be high and your temperature to be low, and that's the thing that will give you the highest capacity factors. And then we have these energy generation models, and we need to map them onto areas where we have installed capacity, right? So what this figure here shows, ignore the colors, each of these black dots is where we have a wind farm or a solar farm installed across Australia. So we've got, I don't know, 100, maybe a few hundred of these. And each of these dots will have a different amount of installed capacity. So not every wind farm is the same size, basically. And we can summarize how much capacity is installed as a function of latitude or longitude here. This kind of cluster of blue bars, what that's telling you is that the vast majority of our wind power is situated in the southern part of the country. And that's, that makes sense. That's where the mean wind tends to be highest. So that's where we place our wind farms. And also in the western part as well. So it's this kind of southwest corner. So that aligns with the result that I showed you at the start of this talk. And comparatively little going on, even with solar panels, solar farms, we have very little installed capacity up in the north. So what we need to do then is we need to take all of our capacity factor time series that we computed, and then we scale them by the amount of installed capacity across each of these different regions. So we've got really quite a lot of complex information here that we're trying to aggregate into something that makes sense from an impacts perspective. And then we can go back to our relationships with the climate modes and say, okay, well, if we looked at the relationship between ENSO and wind speed, we saw some things that might indicate there's a relationship there. Maybe that has implications for wind power, but we need to go and check this. So these figures show the relationship between total power generated, so that's solar and wind power, versus the Niño 3-4 index. And then the box plots there are just summarizing the data for values that are below -1 or above 1. And if you thought that we had a relationship between power and ENSO from some of the results I've shown you before, then this is maybe going to be a bit of a surprise, because you can see that these box plots across the different panels here, these are almost identical. So what this suggests is that with the current power system, ENSO maybe doesn't matter too much to the amount of power that we can generate. We can do the same thing for the IOD. So here we're seeing very similar looking box plots, right? So in general, the IOD doesn't have a big impact on power generation, except in some cases. So here in Victoria, we can see that we get some quite high power values during a negative IOD event, same across the entire national electricity market, South Australia as well. So although the means look very similar across different parts of the IOD distribution, there is an indication that actually we can maybe generate some really high values, high power during negative IOD. The SAM is a bit more interesting because we do actually see a bit of a difference here. You look at these box plots and you can see that there tends to be a shift down in the mean and in the tails of the distribution if you go from a positive SAM to from a negative SAM to a positive SAM. So this is maybe a nice result in the sense that if we're thinking about the seasonal variability of energy generation, then we perhaps don't need to worry about ENSO or the IOD, which is, maybe quite nice. So it's not panic stations when we get a strong El Nino forecast in the same way that it might be for other sectors. But when we see, forecast of the SAM going in one direction or the other, that might actually have implications for how much power is generated. But we need to break this down further as well. So this is the exact same plot as before, but just for wind or solar power separately. And it's not really a surprise here, but all of the difference comes from the wind power. So when we see variations in the SAM, that brings along variations in the wind power. But when we look at the relationship between SAM and solar power, we see very little difference. So it's not really a huge surprise there that the SAM is having a big effect on the wind power generated, but not on the solar power. This thing happening in Tassie here is just because there was no solar installed in Tas. And another interesting thing that we can try and find from these sorts of figures, so this is looking at the correlation between capacity factors and the SAM index, summarized by latitude, so just averaged across the latitude, or the solid line is the average, and then the shading is the range. And the black dots are where we currently have installed wind capacity. And you can see that we have this kind of opposite relationship, whether you're in the north or whether you're in the south. And this is maybe useful to know, because if all of our wind capacity is installed in the south of the country, and then we get a positive phase of the SAM, which is turning off our wind turbines essentially because we're not generating enough power, well, maybe there's an opportunity for installing a few more wind farms in the north where we can benefit from that kind of opposite relationship. So these are questions that people are looking to try and answer. But it's quite a difficult problem. So this figure is from a paper by Andrew Gunn last year. And what Andrew did was he basically designed a set of optimal wind farms using a clustering technique. So trying to see whether there was sort of a distribution of farms that you could get across the whole of Australia that would allow you to maximize the use of wind at any time, regardless of how strong it was. And these are the kind of clusters that he came up with. You can see the kind of high diversity of different clusters that you would need in the southeast. And this figure shows the number of farms on the x-axis plotted against the wind variability. So what you want is low variability, okay? You don't want there to be a high variation in your wind depending on as you go through the year. And these curves here show different scenarios of optimal wind farms, and this dot shows the current situation. So if you design wind farms optimally, you can reduce the variability in your system. But what Andrew also found, and this is kind of an important result, is if you look at the green curve here, this is showing the monthly variability of wind power for the optimal set of wind farms, hypothetical wind farms. And you can see that even with this optimal set, you see these really strong variations from 1 month or 1 year to the next. So even if you place your wind farms in a completely optimal way according to this clustering technique, you're still seeing this really strong interannual variability. So it suggests that you still are going to have to worry about the way that the climate changes from 1 year to the next when you're thinking about these sorts of systems. And another really nice paper by Ilona Ray Costa, who many of you will know, tried to get at one of the solutions for this, not focusing on the variability of the wind itself, but focusing on the ways that we can build our energy systems to try and mitigate the effects of this variability. So this is a concept called overbuilding, and the idea is that in a fully renewable system, in this top panel's case, this is just wind and solar only. If you want to power your energy network using only wind and solar, you can do it, but you have to build a lot more capacity than you need the vast majority of the time. So in this kind of light shading here, that's showing the excess wind power that's generated, excess wind power generated that you just have to spill. This is just wasted, essentially. But what you get in return is that, it's not shown on this figure, but during periods where the wind power or the solar power is very low, you will still have enough in your system to provide the energy that's required. And you can get a bit more kind of sophisticated with this and think, okay, well, we don't just have wind and solar, we also have hydro, we also have batteries. And then when you take those things into account, then the amount you need to overbuild by is actually a lot less severe than it might look from this image. So this is one method of trying to get around the problem of variability in wind and solar resource. Okay, so in summary, weather resources is not just about extremes. Weather resources is really kind of an impact-focused discipline, and you've got to be thinking about this in a very multivariate, spatially variable way. If you know what compound events are, compound events is going to be a really useful framework for you when you're thinking about weather resources. It's this holistic, bottom-up approach, thinking about the impact first, and everything should follow from there. And it requires expertise across all sorts of different disciplines. So I've given you perspective from someone who does a lot of research in compound events and the impact side of things, but I need help from people who are experts in climate modes and weather systems. It really requires an interdisciplinary approach. That's it. Thanks.